We learned previously that a sensor takes a physical property as input and produces an electrical property as output. A graph that shows the relationship between this input and output is known as a sensor response curve. A sensor response curve can be used to define and understand many different kinds of sensor properties, including some of the most common types of errors that sensors are subject to. We will look at a hypothetical example first, and then we'll look at some actual examples. In the previous video, we learned about a potentiometer as one type of variable resistance sensor. The potentiometer converts rotational angle, the physical input, to resistance, the electrical output. So a sensor response curve for the potentiometer would start like this, with rotational angle as the x-axis and resistance as the y-axis. In a sensor response curve, the physical property always goes on the x-axis and the electrical property on the y-axis. Keep in mind also that a sensor might have more than one electrical property that it can produce as the output. For example, we could have specified that the potentiometer must have a 5-volt input, and then we could have put the voltage on the y-axis instead of resistance. Now, the sensor response curve defines the relationship between these two properties. To get the curve, I have to do an experiment with the sensor. I will start by placing the potentiometer dial at the 0-degree angle and reading the resistance out with, say, a good multimeter. This gives me 1 point on this curve. Then I will move the dial to a slightly higher angle and read the resistance out again. I will repeat this process until the dial is at its maximum position. Then I will reverse the process. Starting at the maximum position, I will decrease the angle little by little, reading out the resistance at each angle. Then I will repeat the experiment again and again. From all of these data points gathered, I can define a number of sensor properties and errors. In this video, we're going to define and illustrate the following errors and properties: range or full scale, zero offset, zero drift, nonlinearity error, sensitivity, hysteresis, precision, accuracy, noise, response time, and bandwidth. First, the difference between the minimum angle and the maximum angle is the sensor range, also sometimes called the full scale. Now, suppose that when the physical property is set to 0, the electrical output isn't 0. Actually, this will in fact be the case for our potentiometer. Even when the dial is turned all the way to the minimum position, there is still some non-zero resistance. This is known as the zero offset. Now, suppose that as I use this sensor and test it over time, the amount of zero offset changes. This is known as zero drift. Zero drift is generally a worse situation than zero offset because I can pretty easily compensate for a known amount of zero offset in the code that I use to read the sensor. But the amount that the zero offset changes over time might not be predictable or consistent, and so it can be harder to compensate for zero drift than to compensate for zero offset. Now, if the points in my test between the minimum and maximum values make an exactly straight line, that's great. It means that my sensor has no nonlinearity error. Or we might say that this is a perfectly linear sensor. But many sensors have a sensor response curve that isn't exactly a straight line. In that case, we can calculate the amount of nonlinearity error. There are three ways that you will generally see nonlinearity error quoted on a sensor datasheet. The first way it could be quoted is in input units. So for this example, I would start by fitting this curve with a straight line. Sometimes this linear fit is made by simply connecting the first and last points, but other times the linear fit is made using a least square error approach. Next, we would take the point on the curve that is farthest from the linear fit in the horizontal direction. Then we quote the nonlinearity in input units. So this example might have a nonlinearity error of 10 degrees, for example. The second way to quote nonlinearity error is in output units. In this case, nonlinearity will be quoted in either ohms or in volts, depending upon what we've labeled the y-axis as. So the data sheet might say that there are, for example, 100 ohms of nonlinearity error. The third way is to quote nonlinearity error as percent of the full scale, which is often abbreviated as FS. So remember that previously we said that the sensor range, the difference between the minimum and maximum input, is also called the full scale. So suppose that the full scale of this potentiometer is 360 degrees, and suppose that we have 10 degrees of nonlinearity error. This nonlinearity error might be quoted in the datasheet as 10 over 360, or 2.7% FS, that is, percent of the full scale. The concept of nonlinearity error is very much related to our next property in the list, sensitivity. Sensor sensitivity is the amount of change in the output that results from a particular change in the input. Now, since the output is on the y-axis and the input is on the x-axis, you might recognize sensitivity as being similar to the slope of the sensor response curve, and that is correct, since the slope of a line or curve is the rise over the run. The sensitivity of a sensor is the same thing as the slope of the sensor response curve. Because of this, only a perfectly linear sensor has a single constant value for the sensitivity. A sensor that has nonlinearity error will have a sensitivity that depends upon the value of the input. For example, it might have a greater sensitivity at lower values of the input and a lower sensitivity at higher values, for example. Okay, now recall that when I was describing the test that we did with the sensor to get this sensor response curve, I said that we did the test by starting at a low value and incrementing up to a high value, and then we did the test in reverse, starting at a high value and incrementing down to a low value. We did this to uncover hysteresis error. Hysteresis is a sensor error that tells how much the sensor response is different when we go from low to high than it is when we go from high to low. We can express it in the same kinds of ways that we express nonlinearity error, either by specifying hysteresis in input units, in output units, or as percent of full scale. Now, I remember when I first learned about hysteresis error myself, I was totally baffled. I just couldn't fathom why a sensor would respond differently in one direction than in the other direction. So I'm going to take a little detour now and show you an example of why a sensor might have hysteresis. This is a type of sensor called a piezoresistive sensor. It's a type of variable resistance sensor used to measure force. Here's how it works. This is an elastomer material that is made of an electrically insulating material, like rubber, for example. Inside this material is dispersed tiny bits of a conductive material, like copper. When a force is exerted on the material to compress it, the little conductive bits get closer together, so the resistance of the material decreases. When a force is exerted on the material in the other direction, or when the compressive force is released so that the material recovers its shape or stretches, the conductive bits get farther apart and the resistance increases. So, by measuring the resistance through the material, we can figure out the force that was used to compress or extend it. Now, when a force is deforming a material, some of the energy is used to deform the material itself and is stored as elastic or spring energy. But some of the material is lost to heat. So when the force is released, some of the energy is released back from the spring potential energy, but some of the energy is not recovered because it was lost in the deformation. It's this loss of energy that causes the hysteresis error. So when we release the piezo-resistive material, it doesn't recover its shape or its position as much as we would expect because some of the energy that was used in compressing it has now been lost and cannot be recovered as the material releases into its original shape. So not all sensors have hysteresis error, but in general, all sensors that involve deformation of a material will have some hysteresis because of this effect of losing some energy to heat when a material is deformed. Okay, now on to precision and accuracy. These two properties are very much related to each other. Accuracy refers to how close the value measured by the sensor is to the actual value. And precision refers to how likely we are to get the same value over and over again when we measure the same quantity with the sensor. So, for example, suppose that we have already created our sensor response curve for our potentiometer. And since we have this sensor response curve, we know how to convert a resistance reading into an angle position. Now, we take the potentiometer and we place the dial at exactly 90 degrees. We measure the resistance out and we use our sensor response curve to figure out what angle that resistance corresponds to. Then we move the dial to some other position, then put it back in the 90-degree position and measure the resistance out again, and use our sensor response curve to figure out what angle that resistance corresponds to. We do this over and over again, and we get a list of values that were all read when the dial was at 90 degrees. If we take the mean of these readings, the difference between the mean and 90 degrees will be our accuracy. The standard deviation of the readings will be the precision. So, suppose that we have 4 different potentiometers, and we do this test on all of them. Suppose the 4 potentiometers give us readings like this. One of these 4 potentiometers is very precise and very accurate. One of them is very precise but not very accurate. One is very accurate but not very precise, and one is neither precise nor accurate. Can you tell which is which? One way to figure this out is to picture these numbers as if they were darts thrown at a dartboard. If the darts are closely grouped together, Then the darts have high precision. If the darts are close to the center of the dartboard, then they have high accuracy. So, for example, this dartboard that I'm showing here is very precise, but it's not very accurate. The darts are closely grouped together, but all of them are far from the center. Here's a picture of a dartboard where the numbers are very accurate, but they're not very precise. The darts, if we would average them, would be very close to the center of the dartboard, but the individual darts are widely spaced apart. This dartboard is showing an example of values that are both precise and accurate. The darts are closely grouped together, in other words, they're precise, and they're also very close to the center. They're very accurate. So now, let's look back at our 4 potentiometers. Can you see which of these is which? This potentiometer is the one that is very precise, but not very accurate. The numbers are closely grouped together, but none of them are very close to the actual 90 degrees that we set the potentiometer to. This potentiometer is one that is very accurate, but not very precise. If we would calculate the mean of these values, it would be very close to the actual 90 degrees. But the numbers are all over the place. There's a large difference between the numbers. This potentiometer is one that is neither precise nor accurate. The numbers are widely spaced apart, and the mean of the values is also not very close to 90. This potentiometer here is the one that is both precise and accurate. Its mean is very close to the actual 90 degrees that we set the dial to, and its standard deviation is low, indicating that the spread of numbers is small. The last 3 sensor properties or errors that we'll look at today don't link back to the sensor response curve at all. They are noise, response time, and bandwidth. Noise refers to things that the sensor measures that we don't want to measure. Most commonly, sensor noise refers to interference that is either electrical or magnetic. We would like the electrical signal from our sensor to come only from the physical property, but this isn't always the case. Think back to what you know about inductance from either your circuits class or physics class. Self-inductance and mutual inductance are effects in which moving electrons produce electrical fields, which produce magnetic fields, which produce moving electrons. Because of this, things like the flow of electrons in nearby wires can cause electrical signals in your sensor that are not due to changes in the physical property. If this kind of noise is happening in your sensor system, you might need to use some kind of shielding to improve the problem. We have to be especially careful about this kind of noise in robotics because we often have sensors located very nearby relatively high power elements like motors. We have to be careful about the potential for electrical noise from the motors to have an effect on our sensors. There are other kinds of noise in which environmental conditions affect our sensor output. For example, there is a somewhat joking statement among sensors engineers that all sensors are temperature sensors. This means that it is very common for temperature to have an effect on the output from a sensor. Most sensor datasheets will specify the temperature conditions under which the sensor was tested. It might specify things like the sensitivity at a particular temperature. The other environmental conditions that often affect our sensor output is the humidity. You have to be especially careful about this with capacitive sensors, since capacitive sensors rely on having a particular dielectric constant, which can be different when water is involved. The response time and the bandwidth of the sensor are both time properties. The response time tells you how long it takes for a sensor to respond to a static change in the input. For example, suppose that you would start with your potentiometer sitting still at a particular angle, and then you suddenly move it to a different angle and leave it there. You might not want to write your code to read the voltage output instantly. You might want to put in a little delay between the movement and the reading. The longer the response time of the sensor is, the longer you will want to wait between the move and taking the reading. Bandwidth tells us how fast the input can change repeatedly, and we will still be able to read the output. For example, suppose you take the potentiometer and turn the dial back and forth at, say, 1 back and forth cycle per second. Your PSOC and LCD screen might do a fine job of following your motion. Now, suppose you start to move the dial back and forth faster, 10 back and forth cycles per second, then 100, and so on. At some point, the PSOC and LCD screen will no longer do a good job of following your motions. It will start to read the amplitude of your motions as being smaller than they actually are. And when you get fast enough, your motions won't be read at all. The bandwidth of the sensor is expressed in hertz, that is, back and forth cycles per second, and tells you how fast the input can change back and forth and still have the output read well enough. Well enough is often considered to be less than 3 decibels of the amplitude of the motion lost.